Well, good morning, everyone. And I also want to acknowledge and thank Thermo Fisher for their generous support for this meeting. It's been tremendously enjoyable, and I am sure today and tomorrow will be equally enjoyable. So today, let me first of all acknowledge people who contributed to the work and the funding and support for our lab. I'm going to go over two areas, and I will try to give you some rationale for why these two areas might be of interest. They have applications in some areas. They may not be appropriate for everything or everyone, but I think it's a good idea to at least know what the opportunities might be. So I'm going to talk a bit about spectral flow cytometry or hyperspectral flow cytometry. You'll see that term being used. And I'll try to explain what its advantages and disadvantages are. Then I want to talk a little bit about high throughput and to some extent high content flow cytometry. And I want to show you what some of those opportunities are. And after the coffee break, Carmen from my lab is going to give you more details as to how you can achieve some of the things that I'm going to talk about in my presentation. So I may not give great detail in how you get to the point of pulling out the data, but Carmen will. So I take us back to 1990, which I did a couple of days ago, and just try to get in your minds that you had a very limited capacity in flow cytometry. You may have been able to do 3 colors, and if you did do 3 colors, it was common to publish a paper saying, I can do 3 colors. Right? Just like Mario publishes papers saying I can do 25 colors or 30 colors. But in the 1990s, 3 colors was serious, and software was not very sophisticated. And the reason was that not many parameters. So it was moderately easy to think about what the analytical process might be, even though it was somewhat difficult to achieve it. And list mode files weren't tremendously large, so we didn't really have big disk drives. It seems ridiculous that you might have an 80 megabyte disk drive, but that was pretty normal. That also might have restricted you, because if you wanted to do a very large, high content or high throughput assay that might take 100 or 200 megs, it wouldn't be possible. One of the data sets that I'll show a little bit about and that Carmen will describe in detail is 0.5 gigabyte for one data set. So this sort of thinking couldn't possibly have occurred then. So, yeah, people published papers saying, I can do 3 colors, and there's many more examples of that. So I just wanted to throw in some ideas. What might you think would be a possibility in the future? Sometimes we look at what we have and we make an assumption that that is the only thing that's available. But there's always something around the corner. So a lot of people don't like the thought that maybe you won't need a technician to run your flow cytometer. In clinical labs, that might be something that they would consider would be an advantage if you could have a fully automated clinical diagnostic system. So people have been thinking about how to do that for years and years, if not decades. So it's a goal. And the question is, will it be achievable? Or when will it be achievable? Could you imagine running 1 million events per second? Again, it sounds a little bit ridiculous, but it only sounds ridiculous if you are thinking based on what you might have in your lab now or what you do on a daily basis. This would have been ridiculous 15 years ago. Right? This concept of having 64 or 128 gigabytes or a terabyte of memory on a device like this was inconceivable 15 years ago. Inconceivable. But it's here today. And you might start thinking, what the heck will this look like in 15 years from now? And most of you will not be able to put any sensible construction to that because we don't actually know what's going to be invented. So the thinking, when we start thinking about the opportunities in flow, we're very much often restricted by what we know we can do at the time. Could you get 3D images as well as normal flow data in an instrument? Could you measure 20 nanometer particle in a flow cytometer? Well, of course you can't. Everybody knows that, right? You never know. Could you measure any colour at all, irrespective of what the colour was? Could you run 20,000 samples a day, or maybe more? So these are things that you might think about. Actually, almost all of those scenarios are almost possible today. It's a bit of a shock, really, when you start thinking that, gee, we're pretty close to doing some of those things. So, let me talk a little bit about hyperspectral and then high throughput. So take a look at this graph. It's very simple, straightforward, 4-color collection. The fundamental basis of how we do most flow cytometry is we take a window, we use optical filters, and we take a window, and inside that window we collect all the photons that come through the flow cytometer that fit in that window. That is, photons that have that energy level get measured in that window. Photons that have that energy level get measured in that window. But when we do that, regardless of what the shape of this curve is, we lose photons. Poof, they're gone. Now, you may be able to recover some of them because you can say, well, I've got some of the photons in the other window that should be in this window, so I'm going to capture a percentage of those and I'm just going to add them to this window or another window, right? And we can do that. We basically call that compensation. So there are ways and means of altering that, but the equation is, it's a fact that you cannot get all the photons that might be related to that probe. You're going to lose some signal. And the tighter you make this window, the smaller you make it, the less signal that you measure. And that's one of the compromises that we're prepared to do in doing flow cytometry. So the question is, what if you could measure any colour without changing filters? And that's what I call, and others call, hyperspectral cytometry. So let me explain a little bit what the origin of hyperspectral cytometry was, because it didn't get invented by flow cytometry people. It didn't get invented by biologists either. It got invented by an electrical engineer. And the particular electrical engineer who was most involved in that is a fellow by the name of David Landgrebe, who was a professor of electrical engineering at my university, actually, at Purdue University. And his problem was that he was an expert in measuring spectral properties of materials. And the question was, what are the applications of spectral analysis? Well, you can look at materials, for example. You can look at all sorts of things that might be related in the field of electrical engineering that might facilitate you understanding some feature of electrical engineering. But since he lived in Indiana, we have a lot of corn, it came to pass that he decided, well, what if we could apply spectral analysis to look at corn crops and determine where the diseases were in the corn? Because if you can find where the disease is in the corn and stop it spreading, then this would be an economic advantage. So he put spectrometers in aeroplanes and he flew them over the agricultural area, and he mapped out the agricultural area, and he determined that he could measure the colour of the corn that was in good shape, because they knew from the agronomists, we have a big agriculture university, it's agriculture and engineering. The agronomists said, this is good corn, this is bad corn, this is diseased corn, etc., etc. And so they spent some years doing this. And then it turned out that there was a decision made to put a satellite up. And the idea was, could we use the satellite to image the Earth? Now, the people that were actually interested in putting the satellite up weren't interested in corn. They were interested in big, square, large steel objects with tracks on them and long things that poked out of the end with like rockets on them, and they were looking for them. And they were looking for them all over the world. And they thought, okay, this will work. So they decided to build a system that would be able to see tanks. And what do you think they used? They used a camera. Obviously, you would use a camera, wouldn't you? You want to see something? You use a camera, because it can take a photo. You can blow that photo up, and then you can have a look and say, that looks like a tank, or that looks like a rocket. No problems. Well, there are problems, because when you're way up there, miles and miles and miles, the resolution isn't so good. But what they did was they decided when they built the satellite, they would always put two systems in. So they put cameras in, and David Landgrebe convinced them to also put a spectrometer. Turns out that one of those two systems worked very effectively and the other one didn't. And you know exactly which one worked, the spectrometer. And it became the Landsat satellite system. And every single one of you have probably used Google Earth or Google Maps. And where do you think a lot of that comes from? It comes from satellites. Now, imaging is better today, but in the 60s, it certainly didn't have that resolution. So that's the history of how spectrometers went into space. And in order then to make this technology work, they had to translate the wavelength features that they got, and they had to work out, what does this feature mean? So they did that by taking photographs at lower resolution and lower height, working out what was there, and in many places they knew what was there because they could image some area and they know that this is soil, this is water, these are trees, these are houses, this is bitumen road, etc. And then they were able to map that. And you see here, this is a picture, it says silty water, red sand, grasslands, pine woods. So by mapping that to spectral properties, they were able to build the system that is in use today. So for many years, spectral analysis has been well known and highly developed. So let's take a look at it from perhaps the way a small child would look at it. Here's a photograph of some Lego blocks. That photograph is taken with a colour camera, so it looks like it's in colour. This photograph is taken from a spectrometer. And the spectrometer only has a 20 nanometer band, 460 to 480 nanometers. And here, 480 to 500, etc., etc. Now, none of these photos look very good. You wouldn't publish any of them. But if you put them all together, what you'll end up with is this. And this photograph is almost as good as the original. And it's completely reconstructed. So these colours they're not real. They're fake. But it looks pretty good. It's a true representation of the original, reconstructed from spectral data. In fact, that's what it looks like. It's just a curve. And just to help you a little bit, I have put in a lot of windows here. Just pretend that each of those is an optical filter that you are able to put into your flow cytometer. So you have 10 or 12 there. So you see, you can translate something from this into this, which is recognizable if you understand how to do it. Right. Now, has anyone ever painted a house? I have, of course. And have you ever had to match the paint? Yeah, what do you do? Well, my wife made me get a saw and cut out a piece of wall and take it to the store to match the paint. And then, then we had to match the paint and then I had to fix the wall. But if you have a paint can and you're really smart, you put a dab of paint on the top of the can and you keep the can forever. And when you need to replace it, you take it to the store. And what do? They colour match. Well, it's not magic. It's spectral analysis. So here's the colour chart. Now, here's a quiz. And the quiz is, how difficult is it to tell the difference between some of these? And can you tell the difference? Well, it depends. If you have two slightly different colours and you put them right next to one another, you may be able to tell the difference. But if you put them apart from one another, you probably can't tell the difference. But if you take these two here and you apply an analytical process to that, you can say, if you have this property, make it purple, and if you have this property, make it blue. Now, that's just a mathematical approach to analysis. And there's lots of ways you can do that. You can make it look like as if it's a dot plot from a flow cytometer, for example. So this is just a dot plot. And it looks like there are populations. Well, those populations are these colours. So you can make an analysis by taking the properties of the colours, even if they're really, really close to one another, and you can separate them quite nicely. If this were a dot plot on a flow cytometer, most of you would be looking at this and salivating and saying, oh my glory, look at all those populations that I have, and look how well they're separated. Okay, so let's take those two. They're pretty difficult to tell, probably from where you're sitting. Where are they? That wasn't difficult. Those two populations are so difficult that, as my father used to say, a blind man on a galloping horse with sunglasses at midnight could tell the difference between those two populations. But they're not that different over there, are they? They're really, really similar. And there they are. And look at the differences between them. They are so far apart that there is clear separation between those two. That's the power of spectral analysis. So you could take a lot of fluorochromes. You could put them onto a filter paper, and this is a picture of it here. It's in black and white. It's not really black and white. It's actually spectral analysis. The information under there will tell us what these dyes are. And in fact, here it is here. So the colours that are in there are reflected here. And then these colours are reflected over there in what I've called a gated analysis. What I've really just done is said separate each of these out and put them into a different box. And actually you can take one of those and you can identify where it is on this seemingly boring looking picture, and then you can determine what that actual colour is without having any colours, because those colours are just numbers. They're just representations of what that colour would be. Now we do this all the time. We heard a talk on Tuesday evening where we saw a lot of animal studies. And these particular ones are fluorescence, but there's a lot of ways of taking complex information using spectral analysis and translating it into something that is entirely meaningful. And there's a lot of different processes that you can use, many of which you may not have heard of. You may never have heard of spectral angle mapper or Fisher linear likelihood method. But somebody knows about that, and somebody is using those for perhaps other purposes. And we may be able to take some of those ideas and integrate them into our own technology. So spectral image processing does require some significant knowledge. And there's a lot of things that you need. Doesn't just happen, looks like it does, but there are a lot of processes underneath the hood that you have to understand. But it can be done. Now, one thing that you have to have is you have to have a training set. So you have to know some information about the sample. But once you have a lot of that information, you can deduce from this complex mess what is actually there. So here I'll now compare the two approaches for, say, polychromatic cytometry and hyperspectral cytometry. So in polychromatic cytometry, remember, you take a window, and you can take many windows, and those windows will reflect what is in that population or an environment. And you will extract the photons that fit within the energy level that you've determined here. And in this sample, you will not be evaluating those photons because in this environment, you're only collecting ones that fit in there. And you may have some scatter, some forward scatter, some side scatter, so you'll have some other parameters as well. Now, you can extend this with many lasers and many colors, as you'll hear when Mario and Prateep show us some extraordinary number of parameters that they can collect. There are some problems. And one of the problems is that if you happen to have some probes that are close to one another, you have to make a decision as to how wide to make that window or where to make that window. And that is very tricky, and it takes a lot of knowledge and a lot of effort to do this right. And sometimes you can completely separate things, but sometimes you can't. And so you may make a determination. These two probes cannot be used in the same assay because they have almost identical spectral properties. So you would spend a lot of time making sure that this probe has, this antibody has this probe attached to it, but not this probe. So that is one of the issues. Now, in multispectral cytometry, there's a different approach. Here's the same diagram, exactly the same diagram. What we do, however, is we don't look at a narrow window or a small window. We actually look at a lot of windows, and we create what we call a fingerprint. It's actually almost identical to the way your cell phone works when you put your finger on it. It's recognizing your fingerprint as you. That's pretty clever, but it's well-known technology. And so this, now, we can make this a fingerprint. What is important here is that intensity is not a critical parameter. That's quite different from polychromatic flow cytometry. If you have no intensity in a signal, you can't measure it. And so in hyperspectral cytometry, some aspects will have very low intensity, some will have very high intensity. But if you put it all together, you have a signature. So here is an instrument that we built many years ago, and here's the interface to the instrument. This is equivalent in wavelength here from 400 to 800 nanometers. Here's a cell going down through the flow cytometer. And when the laser hits that cell, it generates a signal. And that signal is the fingerprint for that cell. So there it is. And that's what we call a hyperspectral signature. Now the goal is to try to match that signature. When you put your finger on the phone, it either matches your signature or it doesn't. If somebody else puts their finger on the phone, it won't match. My understanding is that you could pass the phone around to everybody and no one else's finger will match. If that weren't the case, we'd all be in deep trouble because our fingerprints would then be in the FBI database probably somewhere. and we don't want to be in that. So we have this ability to pull out data. So the idea is a little bit different here for polychromatic, where we have to have a number of channels of restricted capacity, and here we take as many channels as we can possibly fit. Now, it's not a huge number, and there's reasons for that. What we actually do is collect 30 to 40 channels. Let me give you a couple of examples from imaging, because imaging is really easy to understand. Here's a conventional RGB image of some cells. Now, if I take that and I apply a spectral image map to it, I can actually pull out different properties. But if I now look at the spectra themselves, and I look at that spectra and say, where are the differences? If I do this manually, and you can. You don't have to do it manually, and you shouldn't. But I want to do it manually because I want you to see how applicable this is to many environments. I can look on here and I can say, look, there's a difference here and there's a difference here. If I were to take those areas and say, what is the differences here between these three curves, it would come up and tell me that there is something different in here. And that is true. Those are GFP expressing components of this cell. And there they are there in the other image. You cannot tell the difference between these and here or here. But in spectral analysis, that is very, very clear, because mathematically this is so different in terms of these curves that you can pull that out. Here's another example. So here we took lymphocytes. We used two different dyes, two green dyes. And we labelled one tube of lymphocytes with dye 1 and one tube with dye 2. Then they were washed and then mixed together. And then they were put on the microscope. But each of those two dyes has these two properties. Now, just imagine, they're both green, by the way. They're as green can be. You see that they overlap. Now, I'm going to be a little tricky, and I'm going to change the colour of one of them so that we get the idea that there's two different curves there. So one is now red and one is green, but they're both green. So what happens now if we apply different windows? It doesn't matter which window you put. It does not matter how wide the window is or how narrow the window is. If you were to run these on a traditional flow cytometer, you could not tell them apart. Under no circumstances could you tell them apart. Because in all cases, the photons are going to be equal in each window. But if you apply spectral analysis to this, why? Because there is a difference in the properties of these dyes, even though they're both green. And when you apply that, you can say, show me all the cells that are this dye and show me all the cells that are this dye. And then you find out, using a cell fingerprint, that these two cells were stained with this dye and the rest of them were stained with this dye. Now that's very clear. You can separate dyes that are even extremely close. Here's another example. Here we have some imaging, and one of the problems with imaging, as many of you know from tissue imaging, is autofluorescence. How do you deal with autofluorescence? Well, what you can do is you can create signatures for the properties of the things you're looking for. You can create a signature for autofluorescence. You can create a signature for background. You can create a signature, in this case, for GFP. And when you put them together, the GFP, which in the raw image simply cannot be separated because the overlap here is 100%. But when you do spectral analysis, you can clearly separate out the autofluorescence and the GFP. So that's a big advantage. So what we're saying is that one of the reasons for doing spectral analysis is to separate out spectrally overlapping stains. So then what you can do is spectrally barcode. It's just a nice word for saying it's a fingerprint. And the idea is that you have the potential for unmixing many, many stains in a single particle and determining what autofluorescence is. And then you have a potential of putting this into an intelligent processing system. So if you take some complex flow cytometer, this is a Partec instrument, in fact, you can see that in this case there's 14 PMTs, they're the red dots, and there's 41 filters. There's the yellow dots. The difference in the design of a spectral flow cytometer and a traditional flow cytometer is that you have a spectrometer and a multi-array detector. That's it. So what can you do with that? So this is the system we built originally. What we did was we put a 6 PMT unit here, just so that we had a clue what the signals actually meant, because you don't have a clue, you don't know. If you're doing spectral analysis blind without some background knowledge, you can't do anything. So you have to have, as I said, you have to train the system. So in order to train the system, we put in a regular 6 PMT system, and then we put the spectral system here, and we divided the signal into two. Many people told us this would not work. There's not enough photons. There's plenty of photons. This is not a problem. So then you get a signal, and then you build a fairly complicated system, and then you need many people to run it, and they rejoice when it actually works, which is what prototypes are about. So this is how this system works. Here's your cell, here's your flow channel, and the cell goes down through there and the laser hits it, and then all the light goes off to a spectral detector, and it looks at what is there and builds a map. Now, if you now look at every single cell, and you look at the spectrum along here, the wavelength, if you have cells that have certain probes on them, or mixtures of probes, then you can actually see them in the system. And then you have to go into a little bit complicated area of putting together a system to analyze that. And I don't want to imply that that's totally easy. It's not, but it's fairly straightforward. So here's a 32-channel detector. It's a little different. It's still got windows. It's just got a lot of windows, and they're not so far apart. And they're all coming from something like that. And you run a cell through, and you might get this signal. You run a different cell, you might get that signal. So you can see that they're very different. Now, this is 32. We just built a 42-channel system. We could go up to 64. We'll keep going until there are no more photons. So we'll see how far we can go. But that's the way it works. Just pretend these are sort of individual PMTs, but they're giving just a spectrum. So let's take these dyes. All these dyes have the same spectrum. They're different chemistries. All come out of Molecular Probes Handbook, or whatever it's called today. I think it's still Molecular Probes. To me it is. So they are, you know, some are better than others, but they are 9 green dyes. So if you do some analysis of those, it turns out that you can separate many of these dyes using a spectral property. Now, I went into Spectral Viewer and I plotted many of these dyes. Some of them are not there, so there's only like 7 of them or 6 of them here. But look, it really doesn't matter where you put your window. They are all going to be green dyes. You put these under a microscope on a cell, they look as green as green. So you're not going to use these with any antibody conjugated to anything that falls between 500 nanometers and, say, 600 nanometers. Because if you do, you're going to have a real difficult time in separating them. But using some deconvolution techniques, we separated 7 of those 9 green dyes. And here you can see them separated. You might say, well, that's not brilliant. Well, this is a very difficult experiment to separate because they're all the same. They're almost chemically the same, just slight chemical differences. I wouldn't recommend this experiment to anybody, but it's a good experiment to demonstrate the capacity of a system. If you needed to use one of these dyes to look at a functional property of a cell, while at the same time looking at some phenotypic property for a marker that you might have, you could do it. But you couldn't do that on a traditional polychromatic flow cytometer because you couldn't separate them. Even if you use different lasers and different things, they have absolutely identical properties, you can't separate them. You can on a spectral system. So here's another really clear example. So these 3 dyes are heavily overlapping. Now, you would take a window, maybe if you take a window here, but you can't separate these 2. So this would be a pointless experiment to do. And you wouldn't be able to resolve them, because if you even used some traditional analytical tool to separate the colors, it's not going to work. But in this case, because the spectra of these are different, they have many properties that are different from a mathematical perspective, you can separate them perfectly well. Look at that. There's no gating. No gates, just looking at the data saying what's the difference in the properties for each cell. And so if you apply additional things like gating, you can go a long way. Here's an example of spectral analysis on the Sony spectrometer. I put a gate along there and ran it along the entire distance, and you could see it doesn't matter where you put that gate. Those 2 overlap. So if you apply spectral analysis to that, these have different properties at different places, and so you can separate them. This was, as I said, was done on the Sony spectral machine by Bill Hoon. This is also work from Sony, from someone in the Sony, showing they've done 12-color separation, again, using that same 32-channel PMT. Here's another example that was published a year or so ago, and this is a complicated experiment. I won't go into all the details, but what they were interested in doing was finding these photoconvertible fluorescent proteins, and after UV exposure, finding those cells in vivo. And they had 2 choices. They could use conventional analysis, or they could use a spectral unmixing process. And of course, because it's on the Sony instrument, they can do the spectral unmixing. So here is the conventional versus the spectral analysis. And if you look at the conventional, it's fairly difficult, if not impossible, to separate some of these probes. They have, if not 100% overlap, it's 95 or 98. And you just simply cannot resolve that. So if you go now to the idea of looking at the spectra, it is possible to resolve them. And in fact, when they did this resolution, they were able to extract all of these probes by using intelligent spectral processing. So you can look at lots of biological features. You have a system that I would contend is much simpler in mechanics, less components, and it does have to do the equivalent of compensation, but I would contend is more standard and easier to apply. And I think it's a good opportunity for building some panels. Now, I've sort of given you the advantages. What are the disadvantages? Well, obviously you can't do it unless you have a special instrument that has spectral detection system, and the bands are very narrow, so you may get less signal to noise per band. That's a fact. You can't get around that. And there are some wavelength dependencies. You have to have enough bands in the width of signal that you can collect between your laser excitation that you can collect a number of bands. And there may be noise issues that you have to deal with. It may be a little slower. You may have more complexity with multiple lasers. So I'm not suggesting that there aren't complications like there is with any technology, but many of those can be overcome. So that's one approach. Now, last 10 or 12 minutes, I'm going to talk a little bit about the second part, and that is high throughput analysis. So spectral can sort of be considered as a high content because there's a lot of information that's there. But we'll sort of differentiate between calling that high content and having a large number of parameters. I'll discuss that in a moment. So traditionally, flow cytometers were designed to run with test tubes. And then eventually, people started putting on microtutor plates. And so probably every instrument now can collect a microtutor plate. But they weren't really designed that way. If you think about the design of flow cytometers for many, many years, they were really designed to collect a sample and analyze the sample. And if you needed to divide up the sample into 10 or 12 or 15 pieces, then you would do that. And what that meant was that you had to try to then work out which combinations of files are related to this assay and package them. In the imaging world, they were a little bit smarter than we were in the flow world. In the imaging world, if you did a confocal image and you had 100 image planes, they didn't give you 100 files. Because if they did, by the end of the day, you'd have 10,000 files sitting on your computer, and you would have to work out what the heck was this file. So what they did, well, they're really smart. They said if this is an assay, and these 100 files are actually in one file. And underneath that, they structure the file. It's a clever thing to do. We didn't do that in flow cytometry. We made 100 files. So it can be a little bit tricky to do the analysis. Database management. Are you kidding? Some people are doing it now because you have to if you're going to collect complex and large amounts of data. FCS standard. Again, it's just a matter of how many standards there are when companies build their software. It's really good to have a standard, but every company says, well, but I have a better idea for this, and I'm going to put that into the standard. And so it's close, but not quite. The advantage of moving to plate-driven systems is that, at least in the instrumentation side of it, if it collects a file from a 96-well plate, the first one is probably going to be named A1. It seems reasonable, right? So you could take that data set and you could always identify that it's A1 or H12 or something like that. Okay, so this is how we've operated. We take our samples, we run them, we get data, we repeat that. And this is a very traditional process. Looking at a data set and extracting what it is that we think we're looking for. So we take biological environment, we break it up, and then we put it back together again. Now, high content, or high throughput rather, is not much different. It just is that we take the same biological material. If we have systems that can handle big numbers of samples, then we can actually build a bigger experiment. We can do an experiment with 384 wells that if you didn't have a plate reader, you wouldn't do that experiment. Because if you did, 384 tubes, you wouldn't do that. I don't think anyone would do that. Has anyone done a 384 tube experiment? I think it would be difficult. Maybe Prateep would have done that some years ago. But the bottom line is, if we have order, if we have the order here and the organization, there's an opportunity to do things in a much more sophisticated way. Now, when we analyze a data point or a sample, we can go through looking at what's in that tube and analyzing it. The problem is when we have a very large number of data sets, now we have to create a matrix, and that matrix actually gives us some advantages, because now, and in high throughput, this is the only way to operate. Because what happens now is we have a question that we have to answer. And the question might be something simple like, what's positive and what's negative? There's lots of ways of approaching that. And traditionally say, I'm going to put a gate there and I'm going to make this positive and I'm going to make this negative. But, you know, if you had a barrel of apples and you were looking for the green apples, you could sit down and count them, and that would work. It's just that if you had a lot of barrels of apples, that wouldn't work. And so you might look at what does a green apple look like, and what does a red apple look like, and you might then apply some mathematical approach to that analysis. If you have your data in a highly organized way, and it's easily accessible, and there's some relationship between them, then these sorts of approaches can be done. So to collect large amounts of data, you don't put the sample on the traditional flow cytometer. Larry Sklar came up with the hypercyte system, and you put that hypercyte system to a fast flow cytometer, and this is what we have in our lab that we do a high throughput screening. So this robot can sample the 384 well plates. This is a fully automated system we built a number of years ago. Automated incubator over there, and FX robot, and samples can come on the conveyor to here, and then they're sampled and they go in here. So you can go this way or you can go this way. Now, what does that mean? Well, this is time. This is number of 384 well plates. Here's one. And about every 10 minutes, give or take a minute or two, and you can collect huge numbers of wells in a small length of time. Now, you have to prepare these plates, by the way. You need a robot to do that because you can't do it by hand. You also need a robot to analyze them, because if you're going to produce that much data, the analytical process becomes too complicated, too much information. So we sat down and thought about this, and we said, why not just build a graphical interface where all the blocks actually have some meaning, and just bring the blocks together. And so we built what we call a logic map. And most of the things I'm going to show you and what Carmen will explain to you is how that's built and how it actually works. And one or two examples are, this is an assay where, in this case, I'm going to look at these three assays simultaneously on a HL60 cell line. And I'm going to use Plate Analyzer, which is a software package we built to do this. It was primarily built initially just for this purpose, because we were producing a plate in 10 minutes, and then we didn't know if the data were any good. And so you produce a plate having spent hours preparing it, and you have the plate run 384 wells in 10 minutes, and then you sit there thinking, what if it isn't right? What if I made a mistake? Should I rerun the plate? I don't know. So our criteria was within 1 minute after finishing that plate, the technician needed to be able to see the map of all the data with the results so that she or he could make the decision, put the next plate on. And that plate's gone. So that was the criteria. And the idea is you have to analyze the plate. You cannot just look at a single sample. You can if you want to, but that doesn't tell you the answer. You need to have this. And we wanted this entirely in a graphic model, because what we were looking for are dose response curves. And if you run in flow cytometer and what you're interested in is dose response curves, how do you get a dose response curve? So here's the plate. It's a 384 well plate. In this case, there's 16 drugs down here, and there are 10 doses across here. 10 doses, another 16 drugs. So there's 32 drugs there. Over here is a positive control, negative controls over here. And that's the report. That's what you want to know. Did you identify the drugs that have toxicity, or did you not? Are there dose responses? Are your positive controls actually positive? Are your negative controls actually negative? And do you get the dose response curves? So that assay is done here. That's it. Forget this one. These are two different protocols. You see they're on the same screen. You can click on one or click on the other, and you get a different protocol just by clicking on the protocol. But this is it. This is an entire analysis for dose response curves from list mode data. And there's the result. So if you see the result in less than a minute for a 384 well plate, you say, okay, next plate, that's it. Now you can report these data, you have to do that, but that's a separate process because you've got a lot of plates to run. Okay, there's another analytical process. Here's a process. If you want to apply some other rule, if you want to put an operator in here, maybe you have two populations you want to look at and you want to separate them, and here's maybe some drugs you're looking at. This is a full, complete analysis, because this means something, and this means something. It's just graphical display. Now, here's your 384 list mode files. Here's the output, or the analytical process, and here's the output. In real time, it takes about 8 to 10 minutes to run this on the flow cytometer. It takes less than 20 seconds to load all 384 list mode files into the software, and less than 30 seconds to produce the curve. That's it. The goal is to get the results. The goal is not to agonize over the analytical process, because the results count. What are the IC50s for these drugs? That's what we wanted to know. And going back to this same curve, in that assay where there are 3 sets of curves, because there's 3 different assays in the same well, and there's 3 sets of 32 drugs looking at 3 different assays on every cell, if you look at the same scenario with 10 point dose response curves. That's light. We're not just screening for positivity, we're looking at effect. You can see here in, let's say 2 hours, you may well be exhausted, but you've got the analysis of 10,000 wells and 800 drugs in 2 hours. Okay. So I'm not going to go into the details of this because Carmen is going to show you, but I'll preview 1 or 2 things that she's going to be talking about. Here's a 6 or 7 color analysis, and it has dose response curves. And the goal here is to look at the effects of certain drugs on multiple cell populations. So these are the cell populations, and there's the dose response curves. That's the analysis. That's it. So this separates the different populations, and then you put a gate on those and say, give me the dose response curves for each of them. This is one that Carmen's going to show you. It starts as a 500 megabyte file. It has about 45 parameters in it. And you can look at every property of every cell on the screen and click on it and find those properties for a lot of information. 14 phosphorylation states, 14 different populations of cells, and 12 activating molecules. And there's 8 concentrations of the staurosporin, which in this case was the molecule of interest, the drug of interest. So you can separate those and look at them as you would do in a normal flow cytometer. You can identify the populations as you would do in a normal flow cytometer. You can look at all your activating molecules which are in dose responses, which you can't do in a normal flow cytometer easily. And you can just view the data at any point. And that is a logic map, because everything that you want to do is on one screen there. And you'll see we don't look at many histograms or dot plots. You can choose as many as you want here. You can click it here and you can find out what's going on in each one. So the model here is trying to end up with something that's visualizable. We're visual animals. We like to see pictures. We like to see things that have meaning to us. So we have to work out how to make things that have meaning to us. Everybody does that in biology. We create things that have meaning to us. But underneath that, there has to be some kind of analytical engine, and there has to be all sorts of things. So what we want to be able to do is pull out the knowledge that we have, build the pathways of knowledge, and then help us by some interactive process to get to this. And that means we have to have a slightly different approach to our analysis, because we have to have people that have these sorts of skills, that participate with us as scientists. And that really is a core aspect of where we go in this technology. So I've given you 2 opportunities, spectral analysis, and what I've suggested is that there are some alternative approaches that are are unique to a spectral system. I didn't tell you that it's the best system in the world. What I told you is that if you have applications where you need to look at certain probes under certain conditions that you can't do, then you can use that approach. And I always look at using the best instrument for the application that you have. If it's polychromatic, use polychromatic. Thank you. And if it's spectral, use spectral. Now, if you're interested in looking at large data sets, or if in your wildest imagination you could conceive of an experiment that would require you to run 1,000 samples in a couple of hours, you wouldn't think of that experiment unless you had the capacity to actually run them. It would be pretty stupid. But you now know that such capacities do exist and that you could design such an experiment. you will need a fair number of cells, but actually you may not need huge numbers of cells. And those calculations can be done. Now, if you do that, whichever way you do, whether you go spectral or you look at high content or high throughput, you can't sit there and say, I'm going to set the gate here, and I think this is positive, and I think this is negative, and then the next one I'm going to... You've got to move to different approaches to analysis. There's too much data. Can't imagine that in the genomic world, people sitting down and doing it one by one. Doesn't work, because the data sets are too large. So, what you can do, though, is there are ways of putting stuff under the hood. We already do that in flow cytometry. Most of you don't have a clue how you would take the data and measure the coefficient of variation line. You don't have to worry about it. Click a button, say, give me the CV, and it does the CV. You are assuming that somebody knows how to collect a CV or make a CV, or something else, a cluster analysis. You don't need to know that. You press the button to do it. Well, you can do exactly the same thing here. It can be extremely sophisticated and complex. And as long as you understand the right way to apply it, which might need some tutorials on, then it is possible to do that. So with that, I will thank you for your attention, and we'll have some morning tea. Thank you.
Thank you, Paul, and I'm sure that there are a lot of questions.
Yeah, clearly.
Maybe a stupid question, but so HPLC systems, they have also a spectral reader when they treat with fluorescence. If I'm correct, that does a scanning that has much more resolution than...
Yes.
So would that be possible to implement that into a flow cytometry system?
Yep. Ger van den Eng did it many years ago, but you can only measure the spectra of a population of cells. In other words, the liquid volume, but you couldn't do it to a single cell. And if you do it to a single cell, it would take some time, and you don't have time. So the logic of having less number of points to the curve is that you've got to measure them all at the same time. So a spectrometer normally has to scan. And even if you use a very large array, it's a little bit more complicated. And there's a trade-off between the photon availability and the sensitivity of the detector. So you can have an extremely large number of detectors, but the sensitivity then has to be appropriate for the system. Turns out that, at the moment under about 60 seems to work quite well. Maybe in 20 or 30 years that solution will be achieved, and we'll have gigahertz-based detection systems. And I have absolutely no doubt that is exactly what will happen. And I predict within 10 years, there'll be a gigahertz-based array that will do nanosecond resolution, and you won't need any optical filters whatsoever, or spectrometer, because you will measure the energy of every photon, and you'll be able to do it in nanoseconds. So that is the only way I think you could achieve high resolution.
We thought.
Thank you. Not speaking about in 10 years, but today like when you use a spectral analyzer, is the deconvolution of the different spectra an issue in terms of time of analysis? So if we want to be practical, just today, not waiting for some years.
A good question. How do you define the probes that you're going to use? And you have to train the system. So you have to have all the probes. And there's some complications there, because those probes may act differently in different cells under different pH conditions. There's no doubt about that. So those have to be taken into consideration. But what I'm told from colleagues who've used the spectral, Sony spectral system, is that one of the advantages they see is that once they define the spectral properties of certain probes in, let's say, a lymphocyte environment, blood cell environment, or a tissue culture environment, HL60 cells or any other cell that you have, they have found practically that the spectral map of those probes doesn't change from sample to sample to sample. That seems to me to be a real advantage of that system.
And then once you have set up, it goes very fast. You know,
Once you've set it up, it goes very fast, but you have to train.
Okay.
Which can be the price of a toy like that? I mean, which
I
is
have no idea. I have no idea. I built my own.
Okay.
Do you think you'll ever be able to sort with these, or it just takes too long to do the deconvolution?
When we first built ours, we ran the samples and then spent 2.5 to 3 hours working out how to analyze it. But Sony applied algorithms that took us hours to do in microseconds. So probably close to sorting speed. I don't know if Sony's ever managed to get the spectral system to sort. I really haven't followed that. But yes, it will happen. It's just computation. And we know that that's the thing that changes fastest. So eventually, I don't know what it really would mean, though. I don't think I want to do that because it seems like it'd be really hard to do. But it will.
I have quite naive questions, actually, because I wonder if it's possible to distinguish cells with different level of fluorescence. I mean, you know, when you have lower or bigger amount of epitopes on the surface.
Yes. So the question is, how do you distinguish cells that you would maybe call low, medium, high expression? That is an issue that might be a little tricky. I think it's a computational issue, but I wouldn't say to you that it's going to be totally obvious. But there will be some cells that have very similar properties, and one aspect of one color will have a slightly different intensity. When I said intensity is not the key property, what I meant was that in any one color or any one band, it's not critical. But as you pointed out, if you had an identical cell, but in one particular property, there were 2 different levels, in theory, yes, it should be able to pull those out because they will show a different fingerprint. The idea is that every cell has a fingerprint. The question is, can you identify what the fingerprint is, and is it close enough to this fingerprint to say these are the same cells but have different expression of this marker? So that's where you start getting into the details that require experimentation and testing and perhaps modification of the system.
Thank you very much.
Hi, thank you for this wonderful talk. Just out of curiosity, the high throughput system, how long did it take you to set it up? Because it seems like that's quite a challenge, maybe.
Actually, I think it's not as big a challenge. When we first did it was maybe 8 years ago or more, 2008. And when we first got the hypersite, we really struggled to get it to work, but it was sort of early days of the hypersite and getting it to work on our Cyan. I do remember it took us about 6 months of constant on the phone, Skyping. We actually set up a Skype thing in the lab where that was, and we were every single day Skyping. Well, we can't get it to do this, or it's not doing that. And it was a matter of our inexperience with it and being new technology. My understanding is that that's not the case today, that they're much more sophisticated. They've integrated systems. I have a separate hypersite and a separate flow cytometer. Right? So after initially understanding it, we got it to work so well that it caused absolute chaos because we got so much data we couldn't analyze it. And so that's what drove the process. So I think today, if I put a hypocyte and a cyan into a lab, I think within one day or 2 days, I think, okay, I'm not going to say I could get it humming, but one of the techs in my lab could probably get it humming in 1 or 2 days without any problems. So it's not that scary. It's just a robot. It just goes like that.
One more?
It's coffee time.
Yeah, just last one.
Now, this thing of the fingerprint, I was wondering if it's probably easy to distinguish in the blood the different cells, not based on scatter properties, but in this way of the spectral way. I mean, did you try to separate neutrophil to monocytes to lymphocytes or even populations?
Yeah, I mean, you can do the same sorts of separations that you would normally do. But if what you're implying is, completely automated clinical diagnostics, that's called the Holy Grail. And that always seems easy, but it always turns out to be hard. And that's because, my theory is because if you want to apply this to patients, the problem with patients is that they're always sick. And everything's different. So I don't know how that's going to work out. In a laboratory setting where you have, in vitro environment, things are so much more organized than dealing with patients. So that's my theory anyway.
Thank you.
Coffee, please.